Today I'm going to calculate electric field. So I'm going to calculate electric field as well as I'm going to calculate depletion layer width. Depletion expression for depletion layer width, and we see how this depletion layer width depends on applied voltage. So in order to calculate electric field, okay, I already told you that we have charge profile in PN junction. So yesterday we have seen that we have a charge profile. Okay, we have Q and D in P side, and we have minus QNA, okay, at P side. This is P type, this is N type. So I have this charge profile here, and I told you if I want to solve the electric field, I need to solve Poisson equation, which is nothing minus rho upon EC, where epsilon S is the permittivity of semiconductor, and in 1D I can write this is a delta phi upon del x square minus rho upon epsilon C, and I know the electric field is minus negative gradient of potential, so I can write this equation as del E upon del x equals to rho upon epsilons. Okay, now I know rho value in both the regions. Okay, depletion region, both side. So this is I call xn and this is I call minus xp boundaries. Okay, so I know both the charge density in both side. So now I can find the electric field in p region as well as n region. Okay, so what is the electric field between 0 to xn, and what is the electric field profile between 0 to minus xp? So let it calculate in region first. Say region, okay, I want to calculate region 0 to xn. Okay, so del E upon del x, okay, rho upon epsilon s, and rho value is here q and d, positive es. Now let me integrate this equation. So if I integrate this equation, what I'll get? I'll get E, okay, q and d. If I integrate this one, okay, say del E q and d es upon del x. Now if I integrate this equation, this will give me E as a function of x equals to q and d upon es, and a constant say c1 x into some constant c1. Now I know if I am at a boundary, field is only in the junction depletion layer width. Out up, if you go regions beyond the depletion layer, okay, there is no electric field because charge is only here. Charge is only concentrated in this region, so only electric field is here. If you go here, there is E is 0, so here your E is 0. Okay, similarly if you go boundary this side, your E is 0. Here also your E is 0. So applying boundary condition, okay, that x is equal to xn, my ex is 0. Okay, so this will give me the c1 value as minus q nd es xn. Okay, so now my electric field will become in this region, this will become q nd es x minus xn. Okay, this is the electric field in the region 0 to xn. This region, this is my electric field value. Okay. Now, if I put x is equal to 0, if I put x is equal to 0, okay, so this will give me the maximum electric field value EMX equals to minus Q ND. You put x0 here, this will give me Q XN ES. This is the maximum electric field value. Okay. Now same thing I can do for P region also. So P regions varies from 0 to minus XP. Okay. So P region is between, okay, minus XP to 0. Okay. Now here the charge profile is, charge density is negative. So here charge density is negative minus Q Na upon Es. Okay, if I integrate this one, so I'll get integration del E equals to minus Q Na Es x, say constant C2. Okay. Similarly, if I apply boundary condition, if x is equal to minus xp, okay, Ex is 0. So if I apply this boundary condition in this equation, so this equation will give me E, okay, minus Q Na Es, okay. So if I put x is equal to minus xp, this become plus xp, and I put 0 this one, so this becomes C2. Okay, so my C2 will become now, C2 will become minus Q Na Es xp. Okay, and my electric field will become, if I put this C2 value here, so my electric field will become E as a function of x will become minus Q Na Es, okay, x plus xp. This is my electric field in P side of depletion layer. And again, if I put x is equal to 0, this will give me E equals to E max, okay, which will be equal to minus Q Na Es xp. Okay, this is my maximum electric field value. Now since I know the equations, okay, I can plot, we have already done plotting of this electric field, so I can again plot this electric field because I know the equation now. Okay, so if I know the equation, if I plot the electric field here, okay, so I know here electric field is 0, here also electric field is 0. Now there is, now if you put here maximum value is here, this is what, this is a slope negative slope minus qx, and there you have positive slope. Okay, so this is your negative slope, and it boundaries here, it is a maximum. Similarly for n side you have positive slope. Okay, so you can write this is a xn, and your xp minus xp, this is 0, and here you have a E max, maximum electric field, whose value you already know, minus qnd Es xn, or minus q na. Okay, minus q na xn minus q na xp upon Es. So this is the field value.
सर ES क्या है?
ES permittivity of semiconductor है. ES is the permittivity of medium. So permittivity of semiconductor, a medium. So this is the variation of electric field. Now, once I know the electric field, okay, I can calculate the depletion layer width. So there's little bit mathematics there. Okay, so after 2 classes, this will be finished. Then we'll come to our main syllabus of diode, trice, and op-amp. So there are little bit mathematics there, but that is necessary to do. Okay, because many questions are asked based on this mathematics. Okay, based on this fundamental. So there is a need to do this derivations. That's why I'm doing. So now you have the electric field. Okay, now I want to calculate what depletion layer width. So the next heading is depletion layer width. Okay. So once I know electric field, I can calculate now built-in potential as a function of depletion layer width. So I know the electric field EDX. Electric field varies from minus XP to XN. Okay. So now I know what is my XP to 0 electric field. I know. Similarly, I know what is the electric field from 0 to XN E dx. Okay. Now, if you can put the values of electric field here, I know what is electric field. So electric field value is here minus Q ND ES X minus XN. Okay. In 0 to XN and minus XP to X0, my electric field is minus Q NA ES X plus XP. Okay, put this value here and integrate. You will get the required expression what we are searching. So now we can put here minus XP 0. Electric field is P region is minus Q NA. Okay, ES X plus XP plus, okay, I have 0 to XN and the electric field is Q ND ES X minus XN dx. Okay, so now you can solve these things. Okay, so with this expression, what I can get minus Q NA ES. Okay, now I have bracket X, that will become X square by 2. Okay, and then I have a XP, that will become X XP. The limit is 0 to minus XP. Okay, and here I have Q and D ES, and the limit is here integration X square by 2 minus X XN, and the limit is 0 to XN. Now put the limit and try to solve, and let us see what is getting. Apply charge neutrality condition and try to solve this one. Okay, so if I solve this one, okay, shall I erase this one? Solve the integration, put the limits and see what is coming. So if I solve this one, okay,
so 3/2.
Okay, let me check. Okay, so now we are calculating built-in potential VBI. Okay, so I have minus Q NA upon ES. Okay, now if I put 0 here, this becomes 0, this becomes 0. Okay, or okay, and or I'll take what minus common, I'll make this positive. and I put limit minus xp before. Okay, so I put minus xp before, I have taken minus common, change the limit. Okay, so what become, this become xp square by 2, and then minus x. Okay, I have to put minus xp, so minus xp square. Okay, minus xp square, is it correct?
Yes.
Hmm? So this will give me minus xp square. Okay, let me check, some mistake is there.
Minus xp square by 2.
No, no, it shouldn't come minus, some mistake is there. Minus should not come. X square minus q x square.
I'm getting minus 3 by 2 x square.
Wait.
सर
Minus.
आपने माइनस की
Yes. One more thing. When we put VBI, okay, there should be one more minus also, no? EDX. Okay, minus XP to XN. So this minus also should come also there, na? Okay. So this minus also should come there. So this minus, okay. So this minus I'm putting here. You please correct that one, okay. And here also then minus will come. So now this become, and now again minus q and d es. Okay, if I put this one, this become xn square by 2, and I put xn here, so then become minus xn square. If you put 0, then becomes 0. So this will give me now what, minus xp square, this will plus q na es, this become x square by 2. Similarly, this become also plus q and d es, okay, xn square by 2. This is the correct expression. So now if I solve this further, okay, what this will give me, this will give me, if I take common, what I can take common, इसमें क्या common आ जाएगा बता?
1 by 2 q by es.
Okay, so VBI, if I take q common, okay, 2 es common, okay, I can get na xp square plus nd xn square. Okay, and from charge neutrality I know charge is equal to what, na, okay, na xn a, and what should I write, na xn a, what is charge density, length in volume, and q. Okay, so q, so charge is this both sides, so q and d xn a. Okay, q cancel, a cancel, so I have a charge density na xp equals to nd xn. We yesterday we seen that one. Okay, now you can use this one and replace use xp, so I can write vbi will be equals to q upon 2 es na xp. I can write nd xn, then I have xp also here, then here I have nd xn square. Okay, now if I take nd xn common, it's all I'm doing to bring the depletion layer width in picture. Okay, so VBI, this will become Q 2 ES. Okay, NDXN take common. You take NDXN common, here you'll be a XP, and here you will have a XN. Okay, so my VBI become Q 2 ES ND XN W. Okay, where W is the width of depletion layer, W V equals to xn plus xp, that is depletion layer width. Okay, now let me do some more simplification. I can also remove xn, because xn and w together cannot be there, so I have to remove this xn also. Okay, so what I can do, I have this W is equal to xn plus xp. Okay, and I know that ndxn plus ndxn is equals to naxp. Okay, so from here what I can do, I can put the value of xn. Okay, so xn value I can write W xn value become na xp upon nd plus xp. So W will become now, if I take x, I want xn value, na xn value, so I have to put xp value. Okay, I'm replacing this xn in terms of W, so I have to remove xp. So I can write W, okay, xn like keep like this, xp nd xn upon na. Okay, so xn will become 1 plus nd upon na W. Okay, now if I solve it further, this will give me W is equal to xn, this will give me na plus nd upon na. Okay, it's simple mathematics. Okay, no need to be afraid. Okay, now I know this thing W value, I need to put W value here, xn value here. So I have xn, value from here, W na plus nd, plus nd. Okay, similarly if I replace here uh, xn, okay, so I can also write my xp like this, v w nd. This expression I will use later. Okay, so these are the expression. Okay, say a b, and this is my expressions. Okay, now I can replace xn here, and I can only get the expression for W from this after solving little bit algebra. Are you getting this one, what I'm doing here? Okay, it's not a much complicated mathematics, simple mathematics. If you once do your own, okay, you'll get everything. So now
Sir, how ND comes there? XP is
here,
equal to W and
if
NA plus N.
that replace, like I have replaced xp na, if you replace xn in that equation, wx plus xn, okay, so the nd will come na. Same equation, if you are
Okay.
W, you have nxp na, so you remove that one, you can get the same equations. Okay, now if I put this W, okay, W VBI, so I can get the VBI, which is built-in potential, equal to, we'll get a very simple expression now, 2 ES ND, and Na, xn value is what? Xn value is Na plus ND, W become W square. Okay, and this VBI become Q upon 2 ES. This I can write what? N effective omega square, and W will be my 2 ES VBI upon Q N effective power half, where N effective is equals to Na upon Nd, Na plus Nd. Okay, effective doping. Okay, or sum of doping, whatever you can say, is Qn effective. So now I have the expression for depletion layer width. Okay, so I told you that if doping level are same, then the depletion layer width is symmetric both side, n side and p side. If one doping is high, okay, then that side, other side, the width become increasing. That other side, this width gets increased. For example, please remember this formula. We're going to use again these three formula I'm going to discuss now. Okay, so if this formula is clear to you, okay, I can solve it more, a little more simplification. So from here what I can write? I can write here, this is W, Q effective. So if Na is greater than Nd, okay, in that case, my N effective becomes what? If Na is greater than Nd, in that case, what become?
And effective becomes ND.
ND.
Nd, very good. Okay. So N effective becomes Nd because Na is, so because 1 by N effective is equals to 1 by Na plus 1 by Nd. Okay. So if Na is greater than, I can neglect this term. So N effective can come Nd. Okay. So in this case, what happens? In this case, if Na become Nd, okay, my depletion layer with formula becomes what? 2 ES Q, and what is the formula? Just now we written, instead of N effective, you can write Nd. Okay,
VBI upon D.
BBI upon Nd. Okay. Similarly, if Na is very high here, so what will become? Xn. You can write this become 1 plus Nd upon Na. Okay. Now, if Na is very high, I can neglect this compared to 1. So this almost become W. That means Xn become your W. And if you try to calculate XP, okay, if you calculate XP, so XP क्या हो जाएगा? What will XP become? If I calculate XP now, XP is your W ND. Okay, so if I take Na common, so Na is very high compared to this one, so this become Na. Okay, and Na again compared to high this one, so this will almost become 0, because okay, so depletion layer will shift will be on only one side. It's okay, so the difference will decide whether it is symmetric or it is one side, but it's a junction. So this kind of junction is called P plus N junction. This type of junction is called P plus junction, where Na is greater than Nd. And if I draw the electric field now for this kind of junction, okay, so if I plot the electric field now for this kind of junction, say this is my minus xp, okay, and this is my plus xn, so xp becomes almost 0. Okay, so what will happen, this side the width will be less and the whole width will be this side. Okay, so this still is negligible and whole width will be in this side. So this is the, here we have a Emax, okay, 0. So this will be a type of electric field for P plus N junction. Similarly, we can show if Nd is greater than Na. Okay, if Nd is greater than Na, in that case your N effective becomes equals to Na. Okay, and the width, this become your equals to Na, depletional width, and your xp, okay, xp becomes 1 plus Nd is high Na upon Nd. Okay, so your xp becomes W and your xns become almost 0. Okay, so you can plot a reverse way. So this is for P plus N junction, profile for P plus N junction. Okay, and you can plot opposite way for N plus P or P N plus P plus P N plus N junction. Okay, so this is called your P N plus junction where N doping is high. Okay, and if you want to plot the field here, you can plot the field here. Okay, here it will be less and full XP will be, width will be always towards P region. So this will become your Xn. This is your electric field. Okay, and this is your Emax. Okay, and this is your for P N plus junction. we can also find the relation between Emax and depletion layer width. Okay, have you written this one? If you written this one, then I can erase. So now I can also find the relation between Emax and depletion layer width. Okay, so I know just now I written VBI. I written VBI is equals to what? Q ND XN 2 ES, and what was there? W. If this expression is correct, Q 2 ES ND XN W. Okay, just now I written this expression, and I know what is Emax. Emax is equals to minus Q ND by ES XN and minus Q NA XP upon ES. Okay, so if I put the value here, I can find the relation between Emax and W also. So if I put this value here, okay, what I can get my BBI is equals to minus half, okay, Emax upon W. And if I only say the magnitude of VBI, so this will become half Emax W. So this is the one of more formula for built-in potential, relation between built-in potential, maximum electric field, and width of the depletion layer. So sometimes they ask question based on this formula also. Okay, Emax will be given or W will be given, VBI will be given. They'll ask you what is the maximum electric field. Okay, so you should write all the formulas in one place. Okay, and go through this one and practice. I have given enough problems in your material. Okay, so this was your depletion layer width. Now let us see how this depletion layer width, okay, varies with the applied voltage. So let me write now the formula for W. Okay, this is W square. Sorry, na? So W square, na? No W. This is W here. W. Okay. Now I know what is W. W. Just now we have written that was what 2 ES by Q VBI and effective. Okay. So this is the depletion layer width. Now if I apply voltage, now this is the case. This is the depletion layer width. Okay, this is the depletion layer width in equilibrium. Okay, this is a depletion layer width formula. Depletion layer width in equilibrium. Equilibrium means so far I didn't apply any potential. Okay, so that is V applied is 0. Okay, so you have a PN junction. Okay, you are bringing in contact and you are getting some W. Okay, so far we have not applied any field to this PN junction. Okay, now suppose I am applying field to this PN junction. I am applying forward bias. Okay, so here you have width and the electric field is in this side direction. Okay, because here you have plus and here you have minus. This is creating electric field in this side. Now you're applying a voltage which will create electric field E applied. Okay, which will be opposite to this direction. Okay, so what will happen now? This depletion layer width will decrease. So depletion layer will decrease. That means your built-in potential will decrease. So with applied bias, okay. So with applied bias, okay, with applied bias, you can write the formula W as 2 ES upon Q VBI minus V upon N effective. Okay, so if you're applying forward bias, this will decrease, and if you apply reverse bias, this will become plus, it will decrease. Okay, so I can write, if I'm applying forward bias VF, okay, so for forward bias, okay, when you V applied is equals to VF, my depletion layer which will become 2 ES upon Q, okay, VBI minus VF upon N effective, okay, and for reverse bias, for reverse bias, okay, my depletion layer will become 2 ES upon Q, okay. Reverse bias means now we applied this minus VR, it will become VBI plus VR, okay. So this is for forward bias and this is for reverse bias, okay. This is general formula, okay. This is V applied. Now if you know V positive, that V minus VF. If V negative, you can write V plus VR. So this is general formula, okay. So this is the formula when you have a forward bias, and this is the formula when you have reverse bias, okay. So width will increase. When reverse bias, this width will increase. In reverse bias, you are applying minus here and plus here. So both inbuilt electric field and applied electric field, both are in same direction, okay. So the width will increase. So this is your VR, okay. So I'm writing by VR. So this is for this is the case. So when you apply reverse bias, when you apply forward bias, this width will decrease. When you apply this reverse bias, this width will increase, and they have effect on current, okay. When we calculate the current of mean junction, these reverse bias uh, and forward bias has a effect on the value of current. We'll see that one now. Now let me see this effect, okay, on energy band diagrams. So if I draw the energy band diagram for PN junction, so see what happens when you apply this biasing. So are you getting what I'm doing here? Any question so far? You will not asking any question, okay. So now let me draw the energy band diagram of PN junction, okay. So PN junction under bias, okay. PN junction under bias, under okay, under applied bias, under applied bias, okay. So when there is a no bias, okay, in that case we know this is my depletion layer width, okay. In equilibrium you have E, this is the P type, P side, this is the N side. So you have a EFP equals to EFN, okay. And this gap is called your QVBI, okay. This is your P side, this is your EVP, okay. This is the valence band of N side, this is this is the conduction band of N side. So this is when this is in equilibrium. This is the equilibrium condition, okay, when V applied is 0, okay. Now what happens when you apply forward bias? So when I have forward bias means now you have P with P is plus is P side and minus is N side, okay. So what will happen, it will, when you apply forward bias, okay, so what will happen now, this width will decrease, okay. So this width will decrease, this width will decrease, now height will decrease, and the new height will be what, Q VBI minus VF, whatever the potential you're applying. And now this here Fermi level also will shift, because if you applying voltage, okay, when you're applying voltage, then current will flow, and in order to current to flow, there should be, okay, gap between Fermi levels. Okay, if there's a gap between Fermi levels, then only your current will flow. So when you connect your P, okay, when you connect with the P with positive and N with negative, okay, so when you're connecting P, that means hole's energy will increase. Minus with means electron energy will increase. So hole's energy will increase when it will go down, and electron energy will increase when it go up. Okay, so now there is a Fermi level of holes are down P side, and the field Fn is above. Okay, so this gap between EFN minus EFP, this time is called your QVF. How much voltage you're applying? Okay, how much voltage you are applying, that will decide what is the gap of this level. Okay, when there is an equilibrium, these two levels are aligned. Okay, and this alignment makes sure that there is a no further charge transfer, or there is a no flow of current. When you apply voltage, now you need to flow the current. That means there should be shift in Fermi level, or there should be some gap in Fermi level, then only your electron can move from here to here. Okay, so this is under forward bias. So this is when this is the under forward bias. Under forward bias, that is V equals to VF. Okay, your width is decreasing. Similarly, if you apply now reverse bias, so what happens? So in reverse bias, now you're doing opposite thing. Okay, now this width will increase. So reverse bias, this Q, now VR will add here. Okay, now this time you are doing opposite your Fermi level, because now you are changing. Okay, you are applying here in reverse bias, you are applying here minus, and here you're applying plus. Okay, so your Fermi level will be somewhere here EFN, and here you will be EFP. Okay, and the gap between these two will be your QVR, reverse bias. Okay, so this is under reverse bias, the width will increase, that barrier will increase. Barrier will increase means built-in potential increases, but if built-in potential increases means your width is increasing under reverse bias. So this is under reverse bias. Okay, V equals to minus VR when you're applying this is the energy band diagram of your PN junction. Okay, so this is PN junction, how energy diagrams, energy scale changes when applying, you apply bias. Okay, any question from here? Okay, so this was your abrupt PN junction. Okay, this was your abrupt PN junction. So now let me give one problem.
सर
हाँ,
एक बार जो फर्मी लेवल का शिफ्टिंग है ना फॉरवर्ड बायस में, मतलब ऐसे ही क्यों होता है वो एक बार प्लीज बताएंगे?
forward bias में क्या होता है, you're applying plus here minus here. Okay, so when you applying plus to plus, okay, that means you are increasing the hole's energy. भी shift तो आएगा ही आएगा ना, शिफ्ट तो आना ही है, बिना शिफ्ट के तो चार्ज करंट फ्लो होगा नहीं. ओके, अभी बात है कि कौन ऊपर जाएगा कौन नीचे जाएगा. So when you give negative to negative, okay, that means you are lifting the energy levels of electrons. Okay, here you are lifting the energy level of electrons, and here you are also increasing the energy level of holes. So holes energy increases when you go down, electron energy increases, become free when you go up. Okay, so when you apply voltage, this gap will come. Now electron can flow. Okay, earlier there was same level, so electron cannot flow. Now electron can go here, electron can go from here to here. Again they can diffuse because the width is decreased. Now you apply VBI equals to VF, this width will become 0. This width will become 0 as soon as you keep the shifting Fermi level maintain. Okay, as soon as you apply the voltage and keep the this level maintained, that is possible, that charge flow continue. That means not diffusion will take place. Okay, so what do we see when we bring PN junction together? There is a diffusion of carriers, and at certain point diffusion stops because of applied built-in potential that create electric field which stops the further movement of charge carriers. Now again applying voltage, you're creating the shift in levels. Okay, you are removing the you're removing the barrier. So once you remove the barrier now, okay, if you apply VF is greater than VBI, then what will happen? This level become about this level. Okay, so electron can easily move here to here, and then it can recombine with this. They can jump and they recombine with the holes. So again, diffusion can take place. Okay. Similarly, reverse happens when you apply this reverse voltage. Okay, in this case, now you are lifting the barrier. Okay, so now electron cannot, because earlier it was barrier, now electron cannot go from here to here. Okay, so this is not possible now. So you are that means there's no current flow in reverse bias region, reverse bias. Okay.
In
Huh.
case of holes, in case of forward bias, we are connecting positive terminal to P side, na?
Yes.
So why Fermi level doesn't lift up? It goes down. Why it is so?
So I'm telling now, if you give minus to minus, battery to battery, okay, negative to if you give minus to electron, this energy gas increases QB. Okay, if you give plus to hole, okay, its energy again increases, but hole's energy is always increases when you go below. Okay, holes cannot travel like this. Hole cannot go from higher to lower level, because this lower level is higher energy. Similarly, electron cannot move from here to here, because for electron this is the barrier. For holes this is the barrier. Are you getting? Holes cannot flow like this. Holes cannot come to, see here energy is high low, but still hole cannot diffuse, because this is the higher level for holes. Similarly, electron cannot move from here to here, because this is the higher barrier for electron. Okay, so holes energy you write here, holes energy decreases, increases. Okay, holes energy increases when you go down. Okay, similarly electron energy increases when you move up. You remember these things. Okay, and then with you can explain the diffusion of charge carriers. So this was your PN junction. Okay, now let me solve one problem. So you have been given one problem: calculate the maximum electric field. Okay, calculate Emax, calculate the Emax and W of the region. Okay, for zero bias, there is no bias. For zero bias, that is V is equal to 0, you have to calculate E max and W. For that, you have been given Na equals to 10 is to power 19 per centimeter cube, and Nd is given 10 is to power 15, okay, per centimeter cube. Okay, what do you want more? Ni is given 1.5 into 10 is to power 10. Okay, the ER is given 11.9. Okay, dielectric constant of material, and E naught also given. E naught is given 8.85 into 10 raised to power minus 14. Okay, farad per centimeter cube. These values are given to you. Now you want to find the depletion layer width. Okay, you can take temperature 300 Kelvin. So you want to calculate E max and W. Okay, so first we'll calculate W. Once we know W, okay, VBI, so we know E max is what? VBI is what? VBI is your half E max W is a formula. Okay, if I know VBI, I know W, I can calculate E max. So I will calculate VBI and I will calculate W. Okay, so what is the formula for VBI? What is the formula for VBI? What is built-in potential?
KT by Q ln NAND upon Ni square.
Very good. Okay, so you know the formula for VBI. So formula for VBI is KT upon Q ln Na ND upon Ni square. So Ni is given to you, Na is given to you, Nd is given to you. You can find temperature is given to you. Okay, you can take this kT by q equals to 25 milli electron volt or 0.025 electron volt. Okay, so you can find this VBI. This should come 0.89. This approximately should come 0.89. Okay, you can check the calculations. Once you know the VBI, okay, now you can calculate depletion layer width. The formula for depletion layer width is what? W. क्या formula है? 2ES
upon
Q
Q
VBI
upon
and
N
effective.
effective.
N effective. Okay, so you have Na and D. You can find N effective also, and VBI you have calculated from this equation. For ES, how will you calculate?
R by E naught.
Okay, so you have this is called ES upon this. Is this correct? Okay, so you can find ES equals to E naught ER. So you can write here E naught ER, and you can calculate the W. Okay, once you know the W, you can find Emax from this equation. Okay, because other formula for Emax will not work here because you have not given Xn and Xp. Okay, so Emax formula, you have a formula Xn and Xp, but that is not given. So we're using this formula. You can find your value of. Okay, so the width value I'm writing, you have to check what is the value of W. So W value is coming, okay, around 1.037 micrometer. Okay, that is 1.037 to 10 raised to power minus 6 meter, and
Sir,
maximum
ER value is 11.9.
11.6. Yes, 11.9. Sorry, yes, 11.9. ER value is 11.9, and the Emax value, okay, Emax value is equals to 1.58, okay, into 10 raised to power 4 volt per meter. Okay, so please check it, this one. Okay,
सर
हाँ,
ER का फॉर्मूला क्या है सर?
which formula?
ER equals to ES by
E naught. Okay, and E naught value I have given to you. Okay, 8.85 into 10 raised to power minus 14. Okay, I'm not starting new topic now. This will take time. Okay, so you have any question, please ask.
एक बार वो बता दीजिए कौन से बायस में इलेक्ट्रॉन एनर्जी ज्यादा और होल्स
कौन से बायस में
इलेक्ट्रॉन एनर्जी ज्यादा हो जाती है और होल्स
this में PM forward bias में. If you have a forward bias, okay, so in this case, okay, what happens? Your electron energy go up. Electron energy go up. So your band diagrams. So initially your band diagram is like this. Initially you have equilibrium. You have both EFP is equals to EFN. Okay. So when you apply this field, what happens? There should be a gap. Okay, this gap decreases. Actually, this is no bias. This is no bias. Okay, now when you apply, this gap decreases. Okay, in this case, your FP is down and your FN is up. Okay, EFP is down and EFN is up, and the gap between these two is your applied voltage. Okay, QVF. And the reverse bias is forward bias. Okay, and reverse bias, opposite happens. Reverse bias, this height is increases and your EFP go up. EFP go up and your EFN is here, and the gap again, gap is your QVR. जितना गैप इनके बीच में आएगा उतना ही बिट बढ़ेगा. That is addition to VBI. Okay. So this is the expression. Now when we'll explain the conduction, that time I will again come back to here and we'll discuss how conduction take place in PN junction. So I'm stopping here. You need to solve and send me the solution. Okay, I already given you the answers also. Okay.
Thank you, sir.